In the last video, I talked about arrays and creating arrays in MATLAB. Once you've created your arrays, though, you still need to be able to use them effectively. One important thing that you'll need to do is to extract specific elements from the array if necessary. For example, in the previous video introduction, I mentioned that it would be appropriate to save a rocket engine's chamber pressure measurements in an array. Using this data later, however, will likely require you to examine particular elements in the array. You might want to find the maximum chamber pressure during the test and at what time it occurred. In the previous video, I pointed out that the elements in an array are specified by the row and column numbers in that order of the element. In MATLAB, the row and column numbers are placed in parentheses after the array name. The row and column numbers must be separated by a comma. Numbering of rows and columns always starts with 1. Elements of one-dimensional arrays can be addressed by a single number if you want. If the array has a single column, use the row number. If the array has a single row, use the column number. These conventions are true regardless of whether you're creating an element in an array or accessing an element of an existing array. The only difference is that if you're creating an element, the array element is on the left side of the assignment operator, while if you want to use an existing element of an array, the array element's on the right side of the operator. Suppose that this array already exists in the workspace. I can extract the element in the third row and the second column, this value here, by placing 3, 2 in parentheses after the variable name. This syntax is equivalent to the number 6, which I've assigned to the variable c. The point is that the number at this location in the array can be used just like any other variable. We're just referring to it by the array name and its location in the array rather than a variable name that's unique to this number. Colon notation can be used to access ranges of elements in an array, much in the same way colon notation was used to define ranges of elements in the last video. The approach is similar to that taken when creating arrays, but the numbers created appear within parentheses after the variable name, and of course, all of these values have to be integers. We still specify a beginning value, an increment, and a final value. The actual indices are calculated the same way they were on the previous video. The first index is start_ind. Subsequent indices are created by adding the increment to the previous index. You don't have to specify an index, but if you don't, it counts by ones. The command stops creating indices when the next value in the sequence exceeds the value specified by end_ind. A colon by itself returns all of the elements in that dimension of the array. First, I'll do a couple of examples here to show you how this works, and then we'll do some more examples using MATLAB. Here's the array I'll be working with. In order to keep track of what we're doing, I'm going to label the rows. This is the first row, this is the second row, this is the third row, and the columns 1, 2, 3. Now, if I access this range of array elements, in the rows, the first element is 1, the second element is going to be 1 plus 2 or 3, the next element would be bigger than 3, so this takes the first and the third rows. We're looking here and here. This likewise gets the first and the third columns. So we get the elements here, 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 and here. So C gets set to 1, 0, 5, 9. As another example, I'm starting at the first row. I don't have an increment, so I'm counting by 1, so this will take the first and the second rows, this and this. There's simply a colon in the columns place, so it's going to gather all the columns. I should get all of those columns in the first 2 rows. D will be 1, 2, 0, 3, 7, 0. As an example, I'll create a vector named z, which starts at 0, has increments of 0.1, and ends at 1. Now I'll use colon notation to access specific elements of the array. I'll extract the elements of the z vector that have even indices. So I'll type z underscore even, which will be my new variable, equals z of 2 to start at the second index, incrementing by 2, and going to the end. End is an easy way to get the address of the last element of an array in any dimension. Our new array contains the second, fourth, sixth, and so on elements of the original Z array. When you're working with arrays, you always need to be aware of the difference between the indices, which tell you where the numbers in the array are located, and the values themselves, which are the actual numbers in the array. One reason for this is that the indices in the array have to be real positive integers. Remember that the first row and column in an array are always numbered as 1. Subsequent rows and columns will increment by 1. The second column is column 2, the third is 3, and so on. This might seem like a case of stating the obvious, but this convention isn't universal. In the C programming language, the first index is numbered as 0, and in Fortran you can define negative indices. Anyway, there generally aren't those types of restrictions for the values in the arrays. You can usually assign any number to an array location. There are some exceptions to this if you define a logical variable or a string, but we won't worry about those just yet. For example, the designation A with 0.3 in parentheses after it tries to get the 0.3 element in the array. No such element exists, and you'll get an error message. It is, of course, perfectly legitimate to assign the value 0.3 to an array location. For example, the fourth element of the array A can be 0.3. Now let's go through a few examples of accessing elements of arrays here, and then do some examples with MATLAB. As another example of accessing elements of arrays, I'll talk about using arrays to define indices for other arrays. Suppose we have these two variables defined in our workspace. If I execute this command, the array B is put in as the indices of array A. These values are used as indices. So the first time through, I look for A of 3, which is negative 12. That's going to be the first element in the A array. The next one will be A of 5, 1, 2, 3, 4, 5, which will be 8. And the last one, a 2 will go in here. I'll pull out A of 2, which will be 7. Now let's look at another command. If I say C is equal to 1, 0, negative 3, and then try to access A of C, I'm okay with the first element. 1, A of 1 is 0. However, A of 0 isn't defined. MATLAB doesn't know what to put in there. A of negative 3 isn't defined. This command will simply result in an error message. The next example illustrates how MATLAB can be used to represent and reference some experimental data. This data provides the sound speed in water as a function of temperature. There are really two types of numbers here. The first set of numbers is a group of temperatures, and the second set is a group of sound speeds. It makes sense to assign these two types of numbers to different arrays. So I created an array named temp, which contains all the temperature values, and another array, SSPD, which contains the sound speed data. Notice that I maintain the same order of numbers in each of these arrays so that the first element of the temp array corresponds to the sound speed provided in the first element of the SSPD array. The second elements correspond to a pair of data, likewise with the third, the fourth, and the fifth elements. This is important because if I want to relate the numbers in these two arrays, I have to do that by their positions in the arrays. These two arrays really don't know anything about each other. I have to keep track of what corresponds to what. Now, suppose I want to display the sound speed, which corresponds to the temperature at 180 degrees Fahrenheit. First, I need to find the index of the 180 degree temperature in the temp array. That's the fourth element in the temp array. So to find the sound speed at that temperature, I go to the fourth element in the SSPD array. So I type SSPD of 4, and the number 5095 will be displayed. Next, what I'd like to do is find the temperature which gives the maximum sound speed and what sound speed that is. The maximum sound speed can be found just by looking at all the sound speed numbers and picking the largest. It's 5101, which is the third element in the SSPD array. The temperature corresponding to this sound speed is the third element in the temp array. So if I want to save these values as separate variables, I can assign SSPD underscore max as SSPD of 3. So this will get assigned 5101. And temp underscore max is temp of 3, which will save the 160-degree temperature. This is a pretty simple example, and it's much simpler to do this without using MATLAB. So next, I'll do a more realistic problem using MATLAB. In this example, I've measured a voltage in an electrical circuit as a function of time. I did the measurement using an oscilloscope, which allowed me to save the voltages and the corresponding times at which they occurred. The oscilloscope I was using allowed me to store the time and voltage values as ASCII data, and I saved the resulting files in MATLAB's current working folder. I want to find the maximum voltage and the time at which this voltage occurred. The file containing the time data is named time.txt. I can import this data with the load command. Just type load space, the file name, time.txt, a space, dash ASCII to let the load command know that it's expecting ASCII data. The file containing the corresponding voltages is called volt.txt. Load this file by typing load space volt.txt space dash ASCII. Now I've got two variables, time and volt, in the workspace. Sadly, it'll be hard to find the maximum voltage value and it's indexed just by scanning down the values. For example, if I display the voltage values by typing volt and pressing enter, I get this mess. MATLAB has a function named max that finds the maximum value in an array. I'm guessing that I can use this function to find the maximum voltage, but I also need to find the index where the maximum voltage is found. This index will let me find the time at which the maximum voltage occurred. Let's check the help files to see how to do this. Type doc max. It looks like max will return both the largest element in the array and its index with this syntax. So to get the maximum voltage and its index, I can type max volt, comma, max end. Those will contain the voltages and the indexes, equals max of volt. The maximum voltage is about 1.53 volts, and it occurs at the index location 65. To find the corresponding time, just type time of 65. The time is 0.32 seconds. That was my introduction to array addressing and accessing elements of arrays. In later videos, we'll use these concepts repeatedly. Being able to work with arrays is essential to numerical analysis. So if you spend some time now getting used to these concepts, it'll simplify your life later. However, before I do anything else, I need to talk about arithmetic operations using arrays. In the next video, I'll use the dotted operators that we talked about earlier to implement operations between arrays.